In Math 20-1, we're looking at topic 9.2, solving quadratic inequalities. This is going to be part A. You can write quadratic inequalities in one variable in one of the following forms, where ax squared plus bx plus c is less than 0, where it's less than or equal to 0, where it's greater than 0, or where it's going to be greater than or equal to 0. Remember that a, b, and c are real numbers and that a cannot be a 0. You can solve quadratic inequalities graphically or algebraically. In part A, we're going to be solving them graphically. The solution set to a quadratic inequality in one variable can have no values, can have one value, or it can have an infinite number of values. Well, what is that going to look like? Well, here we have ax squared plus bx plus c is less than or equal to 0. Well, anywhere along that graph is going to be greater than or equal to 0. The minimum point is above 0, so there is no values on that graph where it's going to have a value that's going to be greater than, or pardon me, less than, or equal to 0. Here we have ax squared plus bx plus c is less than or equal to 0. At this time, there's going to be only one point, and that's going to be right where it touches along the x-axis. That's going to be one solution. And then we have an infinite number of values. That's where our graph is going to be something like ax squared plus bx plus c is greater than or equal to 0. And every point on that graph is going to be greater than or equal to 0. So let's look at example 1. Solve a quadratic inequality of the form ax squared plus bx plus c is less than or equal to 0, where a is going to be positive. So if we solved ax squared, or x squared minus 2x minus 3 is less than or equal to 0, simply factor our equation to find our roots. And we've got x squared minus 2x minus 3 is less than or equal to 0. That'll factor into x minus 3 times x plus 1 is less than or equal to 0. Now, if we looked at x minus 1 times x minus 3 times x plus 1 is equal to 0, you'll notice that the roots are going to be at x is equal to 3 or x is equal to negative 1. And the graph is going to open upward because it's a positive x squared. So we know, it doesn't matter what any of the other points are, we know that the graph is going to open upward. Now we can look at this graph and determine where is this going to be less than or equal to 0, over what intervals. Notice that when x is going to be between negative 1 and positive 3, where I put the yellow line, that is where the graph is going to be below our x-axis. It is in the zone where y is less than 0. So every point between negative 1 and 3, that graph is going to have a value that's less than or equal to 0. So what we're going to say is our graph is less than 0 when x is less than or equal to 3, or x is greater than or equal to negative 1. You can graph y is equal to x squared minus 2x minus 3 on your calculators to confirm your results. Now you can take a test point. Let's say x is equal to 0. When x is equal to 0, you're going to get x squared minus 2x minus 3 is less than or equal to 0, and you're going to find that x is equal to negative 3 is less than or equal to 0, which of course is true. Here we have example 2. We're going to solve a quadratic inequality where the form is ax squared plus bx plus c is less than 0. This time it's just less than 0. And a has to be less than 0, so a is going to be negative. So we're asked to solve negative x squared plus x plus 12 is less than 0. If I divide both sides of our inequality by negative 1, I'm going to get a positive x squared minus x minus 12 is greater than 0. So I've changed it. By dividing it by -1, we change the direction of the inequality sign. And now we can factor this into, well, it's got to be x minus 4 times x plus 3. So our roots are going to be at x is equal to 4 and at x is equal to -3. When we graph x squared minus x minus 12, y is equal to it, you're going to find that this graph is going to open upwards because it's a positive x now. And again, where is this graph going to be less than 0? Well, it's going to be less. This graph is going to be greater than 0 when x is less than -3, and also when x is greater than 4. So there you have it. The solution is x is going to be less than, not equal to, just less than -3, and x is going to be greater than 4, not equal to. All right, let's do example 3. Solve a quadratic inequality in one variable. This time it looks a little different. 2x squared minus 7x is greater than 12. Well, if you brought the 12 over to the other side by subtracting 12 from both sides, you get 2x squared minus 7x minus 12 is greater than 0. Then we could try to factor that, and since it can't be factored, well, you know what we can do? We can use the quadratic equation. We can plug in our values into our quadratic equation, and we're going to find that x is going to equal 7 plus or minus root 145 over 4. That's what we'd leave it as if we were going to be exact, but since we're not going to be exact, we're just going to say it's approximately going to be 4.8 if it's going to be 7 plus root 145 over 4, and it's going to be negative 1.3 if it's 7 minus root 145 over 4. That's good enough for what we're doing. We're not asked to be exact. Since this graph opens upward, it's a positive 2x squared. We can draw in our parabola. Now we can see the intervals. So this means that x has to be less than negative 1.3, and x is going to be greater than positive 4.8. And if you wanted to have exact answers, you'd say the set of all x such that x is less than 7 minus root 145 over 4, or x is greater than 7 plus root 145 over 4, and x is any real number. Here in example 4, if a baseball is thrown at an initial speed of 15 meters per second from a height of 2 meters above the ground, the inequality of negative 4.9 t squared plus 15t plus 2 is greater than 0, models the time, t, in seconds that the baseball is in flight. During what time interval is the baseball in flight? All right, well, what we're going to do is going to graph time along our x-axis and height in meters along the y-axis. We plot our points by cheating a little bit, looking at our graphing calculator and seeing where they go. This is going to be what our graph is approximately going to look like. Now, we need to know at what time interval is the baseball in flight, and if you figured out to find the x-intercept, that's going to be at 3.2 and 0. How can I do that? Well, if I set y1 to equal negative 4.9 t squared plus 15t plus 2, and I set y2 to equal 0, and I used my intersect feature on my calculator, I could find that point. Since I know that that's the intersection point, that the ball is going to be in flight between 0 and 3.2 seconds. So I'd say x is all x such that 0 is less than or equal to x is less than or equal to 3.2, and x is any real number, or more correctly, since we're talking about t is less than or equal to 3.2 but greater than or equal to 0, and t is any real number. That's our time interval. Our assignment is to do page 484, numbers 1 to 3. Back with part B.